Okay, so here's another demonstration of the photoelectric effect then. So right now we've got a zinc plate here connected in a circuit with a cell and an ammeter. The cell, notice as well, the cell is set to 0 volts, so there's absolutely no voltage being applied here. Now, at the minute, the light is at 508 nanometers, which is not high enough to liberate any electrons. And you can see that there's no electrons leaving the plate. And again, it doesn't matter how intense the light is, I'm never going to get electrons being liberated at this wavelength. Okay. Now, if I were to then dial down the wavelength, I'm increasing the frequency by doing this, okay, until I hit a certain point, okay. I've got 229 nanometers, I've got lots of electrons being liberated from the zinc plate, leaving the zinc plate and moving across to the opposite side. And again, it doesn't matter what intensity, okay, I'm still going to get electrons emitted, albeit fewer electrons, okay. The maximum energy of these electrons isn't going to change based on intensity either, which is going to further prove light is behaving like a particle in this case. Okay, you can see then that I've got a current flowing now, despite the cell being set to 0 volts. I've still got a current flowing, and that's because there's electrons moving across here. So I've got charges moving across this gap. I can actually use this cell here. So if I was to reverse it and drop the voltage, pop the voltage to maybe minus 1.2 here. Okay, notice that what's happened now, electrons are not making it to the other side. Okay, hence the current has gone to 0. So electrons are still being ejected, but they're being stopped before they reach the other side. So the potential difference is actually stopping the electrons from getting over to the other side, and it reduces the current to 0. What I've found here is our stopping voltage. Okay, so the absolute minimum voltage required to stop all of the electrons moving from one side to the other. Now, I can actually use this experiment here and use this stopping voltage to figure out the maximum kinetic energy of the electrons, and then I can actually use this experiment to work out the work function of the metal and Planck's constant. Let me show you how. Okay, so quick recap. We're going to illuminate this plate with some ultraviolet light. We'll cause some electrons to be liberated from the plate. They will move across to the other plate, and then you'll get a small current flowing. Remember, if you dial up that voltage, then you can actually stop those electrons from reaching the opposite side. And the absolute minimum potential difference required to do that is called our stopping voltage. Okay. Okay, so the stopping voltage then is the absolute minimum potential difference required to stop the electrons from reaching the other side, and therefore it will reduce the current back to 0 again, so you won't get any current in the circuit at all. So if the electrons have got energy half mv squared, so the maximum energy they've got is half mv max squared, we can make that equal to EV, and then V will be our stopping potential here. So EV has come from our voltage equation, okay? If you remember, that was just E equals QV. Lowercase e is just the charge on an electron. So for a single electron, it's got energy half mv squared. We can take all of that away using this stopping potential here, okay, and then they've got to be equal to each other. So we can actually use this stopping potential to figure out how much energy the electrons are going to have when they just left the plate. So you can give the electrons more energy leaving the plate by increasing the frequency of the light that hits the plate, okay? So remember the equation for energy of a photon, E equals hf. If you increase the frequency, you increase the energy. And if you increase the energy, then you've therefore got to increase the stopping potential in order to stop the electrons from reaching the other side, because they'll have more energy, right? So what I'm going to do is I'm going to plot the kinetic energy of the electrons that are emitted from the plate, calculated using this experiment here. And I'm going to plot it against the frequency that the light has upon the plate. Okay, and we will get a graph like so. So initially we won't have any energy at all because the frequency of the light won't be enough to liberate any electrons. So the energy of the electrons will be 0. Okay, now there will become a point when suddenly there is enough energy in the photons to liberate some electrons, and as the frequency increases, the energy that they have increases as well. Okay, and if we trace the line back as well, Okay, you can see that it will hit the axis down here. So where this line hits the axis down here, this is our work function. Well, actually it's the negative of the work function, because this is the negative end of the graph. And you can see that you need to give it this much energy in order to actually liberate an electron from the metal. And then we've got a point here on the graph. This is our threshold frequency. So our threshold frequency is the minimum frequency required to actually liberate any electrons at all. So let's have a look at our photoelectric equation as well, and we can have a look at what we can work out from this graph. So if we look at our photon energy, so each photon is going to have energy hf. We're going to subtract the work function, and then whatever's left over will be in the kinetic energy of the photoelectrons. So we're going to put that over here. Okay, so that's half mv squared. So now if we look at our equation for a straight line, y equals mx plus c. So you can see what's on the y-axis. That is our kinetic energy term. That's this bit here. Okay. You can see what's on the x-axis. That was our frequency there. Okay. And we're left. We can see here already that our y-intercept here is going to be the negative of the work function that we've seen down here, and then the gradient therefore must be equal to Planck's constant. So you can actually figure out Planck's constant using this experiment here. Okay. Now, I appreciate this video has been quite tricky to get your head around, but I will put some questions in the description if you want to have a go at some of those from the Institute of Physics, and I will see you in the next video.